All right, now back to our intuition. That intuition says, let's count the number of links. We call that try number 0. It's the very basic intuition, and we will soon see that is hardly a very useful one when it comes to ranking web pages. Here's a little smarter idea that says, what we can do is to say each node has a certain score. Give it a number. Give it a positive real number. Okay. We're going to denote that number as pi sub node index. In this case, say node 1. So it's got a number denoted as pi sub 1. And another node, say node 2, also has a number pi sub 2. Okay. And here's another one. Node 3 with a number pi sub 3. And our job for the rest of this lecture is to compute these pi's, what we call the importance scores. We can collect them into a vector, pi 1, pi 2, dot, 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 up to pi sub n. This is a very long vector, and by convention it's a column vector. We call this vector pi. Okay. In the textbook or in written media, printed media, you can use boldface. It's hard to draw boldface on the screen, so we're going to just use this arrow to represent that vector. So pi vector, that's what we want to compute. So try 1 says that, look, you got these pi's. Okay. Maybe you can just add up the pi's that points to you. For example, if node 1 and node 2 both point to node 3, then I can say node 3's importance is the sum of pi 1 and pi 2. Okay. Simple enough. This is slightly better than just counting degrees because I now allow each node to have different importance score. Okay. And of course, in general, first node and second node, they may have many other connections coming in and going out. So this is a reasonable choice. Okay. However, what it ignores is that some node, like this node 1 here and 2, they are pointing to many other nodes, not just pi node number 3. So think of a professor who writes reference letters for her students. And if this professor keeps writing that this is the very best student I have ever had in my 80 years of teaching at this university and so on. If every student she writes in that way, and she writes like say 100 letters every semester, then soon people will realize that, hey, this professor's reference letters should be discounted. And that's the idea here, is that you got to normalize by how you spread your importance score. If you point to too many web pages, then each of those web pages that you point to should not receive all your importance. And that is the idea that maybe I should look at the number of outgoing neighbors that I have. So if node 1 with importance score pi 1 points to 3 other web pages, okay, then O sub 1 equals 3, our degree is 3, and I should divide node 1's importance score pi 1 by O1. Okay. So I should be assigning just pi 1 over 3 to each of the 3 outgoing neighbors. And therefore, if you point to more nodes, each of them will uniformly receive pi 1 over, say, 5 instead of pi 1 over 3. And if you only point to one node, then that node receives all your importance score. So let's try number 2 now. Okay, the idea is that we're going to normalize by the spread of importance. It turns out that by this point, we're sort of close to what Google does. In the next 3 modules, we'll have to quantify this intuition and then provide 2 more enhancements. But we're getting there. The idea is that look at all the important scores, add them up across the links pointing to you, but make sure you normalize by the outgoing number of links. Now you may wonder, if I have a node here, number 2 with importance score pi2, I can write pi2 as some combination of the importance scores normalized from the incoming neighbors. Now each of these, say this involves pi1, can also be written as the summation of normalized importance scores from its incoming neighbors. So the question is, on the left hand side I will have pi1, pi2 and all the pi's. On the right hand side I also have all these pi's divided by their outgoing number of neighbors. So I got pi's both on the left hand side and right hand side of this, I guess, linear equation system. Can they actually make sense collectively? Is there a set of consistent scores pi? Is there a vector pi that can satisfy all these linear equations simultaneously? If so, then we have found a particular meaningful and self-consistent way to assign importance scores. If not, then we're in trouble. So the question now is, how can we modify this basic intuition in our try number 2 now in order to guarantee both the existence of such a set of consistent scores and an efficient way to compute these scores?